Hello, I'm Clayton Brown, a Solution Architect for Amazon Web Services, working here in the Sydney, Australia office. Today we're going to take a look at how you can supercharge your applications using graph database technology. Amazon Web Services provides a range of fully managed database offerings. In the relational database category, Amazon RDS, there's a broad selection of both commercial and community databases, such as Oracle, Microsoft SQL, through to MySQL, Postgres and MariaDB, as well as our cloud-native optimizations for both MySQL and Postgres in the Aurora offering. For data warehousing, Amazon Redshift provides a fully managed petabyte-scale data warehouse service in the cloud. And in the non-relational category, there are a number of NoSQL options as well, such as Amazon DynamoDB, which provides a fast and flexible non-relational database service for any scale, and Amazon Elasticache, which provides managed in-memory data stores with both Redis and Memcache engines. Today we're going to take a look at the latest entry to this collection, Amazon Neptune, which provides a new category of graph storage and how you can use its features in your applications. Before I jump in, I want to cover a quick intro of what I'll be covering today. I'm going to take a look at building applications on highly connected data. We're going to look at types of graphs and how to query them. We're going to look at a property graph and an Apache Tinkerpot friend recommendation example, as well as an RDF knowledge graph example. And then lastly, I'll provide an overview of some of Neptune's fully managed enterprise-ready features. So today's applications need to process data that's both rich and highly connected. The data is rich in that it's coming from many different sources. It has heterogeneous data elements and data attributes. And it's the connectedness of these data elements that enable new applications. So if you think about a social network, for example, it's the interactions of individuals with different content and context of relationships which really provide the value of the network. And similar types of things are seen in other recommendation systems. In retail fraud, it's the relationships, such as shared accounts or shared payment mechanisms, that provide the value when building these applications. One of the things about highly connected data is that it's particularly well suited for graph representation. And there are a number of different use cases for highly connected graph representations. So we talked about social networking. There's also various types of recommendation systems. Knowledge graphs are the types of application where you use graph representation to model information that enable customers to improve their retrieval or answer questions about data. Fraud detection applications are also very common. The life sciences is a rich space for graph applications, both ranging from drug discovery to data integration to precision medicine type use cases. And then of course, network and IT operations are fundamentally graph models and structures, so they map very well into these kinds of structures and relationships. So let's look at a couple of examples. Here we have a recommendation graph, and it's showing individuals' relationships between them from a social network context, relationships from a transactional context, and also individual interest models, for example, people's interests in various sports. So representing this information in a graph model, we can start to make recommendations. We can say things like, people who also follow this sport purchase this product. Similarly, we can do things like, for social networks, we can make recommendation based on shared friendships. This case is an example taken from the World Wide Web Consortium, or W3C's knowledge graph webpage, and augmented for this presentation. But we see that we have a picture of a famous artwork, the Mona Lisa, along with information about the museum where it's located, and some further information about the city overall. Then we have some information about users and travel history. Representing this information in a knowledge graph, we can start to answer questions like, who painted the Mona Lisa? What museums should Alice visit while in Paris? And what artists have paintings in the Louvre? Here is a customer example use case from Thomson Reuters, who participated in the Amazon Neptune preview. This is an example quote from their own use case. What they're doing is helping customers to navigate very complex sets of tax policies and regulations, and using a graph-based approach to be able to model these regulations and help customers understand how they apply to them and their circumstance. This is a very interesting use case that we're seeing more examples of. So you've been seeing example applications that you can build over highly connected data. So what are the types of database systems that you can choose for this? Well, you could use a relational database. However, there are some challenges in doing this. Relational databases are generally designed to process information that's highly structured and changes relatively infrequently. The query language is SQL, and if you use this to process relationships in your data, you end up having to process a large amount of joins in your queries, and this makes queries both cumbersome and awkward over highly connected information. The second reason is types of I/O demands. For relational workloads versus graph workloads are very different, and relational databases just aren't optimized to efficiently process graphs. And the third thing that we see in graph applications is customers often want to bring together from many different sources. So they want to be able to flexibly ingest and accommodate data that they didn't initially design their application for. This is a little bit challenging to do in a relational database. So let's look at a specific example about how these models differ. On the left-hand side, you can see a fairly typical ERD or entity relationship diagram, which is a design for a HR example, which was purpose-built to support HR business process. On the right-hand side, we have the same model represented, but as a graph. In here, we can see that the relationships themselves are first-class objects. So if we want to ask questions that we hadn't anticipated, so for example, what are the skills that are particularly needed to build a particular product? To do that over a relational system would be a very complicated and complex SQL query. But to do that over a graph would be a fairly natural expression. So it's really about the models and query semantics which allow you to ask different questions over the data. So what is a graph database? A graph database is a database that's optimized for storage and retrieval of graph data. It supports specialized query languages and APIs that are optimized for graph, and it's tuned for the I/O characteristics that are required to efficiently process graph applications. There are two leading models for graph. The first is something called property graphs, and a property graph has nodes and node properties, as well as edges and edge properties. And the leading framework for processing property graphs is Apache Tinkerpop. It provides something called Gremlin, which is an imperative language that lets you express traversals over your graph. For example, A is connected to B and has a particular attribute with this property. The second major framework is something called the RDF, or Resource Description Framework. RDF is part of a set of World Wide Web Consortium, or W3C standards, collectively known as the Semantic Web. And it has a query language for RDF, which is called SPARQL. So as we're designing Amazon Neptune, we looked at some of the alternatives in the GraphDB space, and what we found was that customers often had challenges scaling up. And so it was relatively common that customers would try a POC or a prototype in application and have quite a lot of success with it. But when they attempted to put this into production, they'd experience a decline in query performance or operational difficulties as they tried to scale up. The second thing that we found was that customers had a lot of difficulty in building and maintaining high availability configurations. So when they wanted to take these applications into production, it was challenging for them to set up and configure these HA features. Further, that these kinds of feature sets were not available in the community or open source editions and required customers to license enterprise editions. Then finally, what we saw was that while there were a number of products that supported both the property graph and RDF models, they tended to do so with a strong bias for one or the other, so didn't give customers the choice to choose the right model for the right application. So with that in mind, we designed Amazon Neptune. Amazon Neptune is a fully managed graph database service. Amazon Neptune is fast and designed for graph applications which need to have very high throughput query answering with low latency. So you can query billions of relationships with millisecond latency. Amazon Neptune is designed to be reliable. It offers multi-AZ high availability, supports further horizontal scaling through read replication, and supports full encryption at rest. So it has the set of enterprise features that customers typically need to put a graph database into production. And it's easy to use by supporting the most commonly used graph models, the property graph and the RDF model. And by providing support for Gremlin and SPARQL, its query languages, we make it easy for you to use these open APIs to access the power of Amazon Neptune. This is a quick view of the high-level architecture of Amazon Neptune. So if you look across the top, you'll see some of the use cases for highly connected graph data. And moving down the stack, you'll see the open source and standard APIs for Property Graph, Tinkerpop and Gremlin, and RDF, SPARQL. Below that, you'll see Amazon Neptune. Amazon Neptune is purpose-built, high-performance storage engine that's optimized for graph. It's both durable and ACID compliant, providing immediate consistency. In addition to the standard and open source APIs, we also support APIs for managing the database. In particular, we offer a fast parallel bulk load of data that's stored within S3, in addition to other database management functionality. Then moving along towards the bottom of the overall architecture, Amazon Neptune rides on a cloud-native storage service. And this is what gives it the ability to offer these sorts of enterprise features for HA, read replication, and encryption at rest. So let's look at both of these types of graphs and how to create and query them. For a property graph, we'll look at Apache Tinkerpop and a Gremlin query. And for knowledge graph, we'll take a look at RDF and a SPARQL query. So you recall that the first model we talked about was a property graph. And so in this is the next level of detail. You can see in a property graph, the nodes or vertices can be used to represent the core pieces of information, much like you would use tables in a relational database. In this case, we have a node which is of type user, and it has an attribute name which indicates it's called Bill. Then we have a second node or vertices, in this case, also a user named Sarah. And there is a relationship between called friend. And there is an attribute on this, which is the date of the friendship. Looking at that friend relationship properties, you can see on this edge, as it's known, we also store information, making this a first-class citizen within a graph database. Again, much like a table in a relational database. So in this example of a property graph, how would you create this type of graph using Apache Tinkerpop? In this example, we're using 3.3, which is the standard supported by Amazon Neptune. And you'll see the example of creating a variable for each user. By creating a vertex or vertices for user 1, Bill, and user 2, Sarah, we can then create an edge or relationship, in this case of type friend, which is what you see on the graphical representation here on the right. So the second model for you, if you recall, are the RDF graphs. RDF graphs are really described as a collection of what's called triples. A triple consists of a subject, a predicate, and an object. So in this case, the subject is something called an IRI, or International Resource Identifier, which provides unique identity. Here we have the example of the predicate specifying the type of the node, which is a user, as per the previous example. And then moving down, we have an attribute or a property, which is the predicate contact name, which is Bill. And that set of triples describes the node we see on the right. Now the third position, we see a triple, the object can be either an IRI or what we call a literal. A literal in RDF is very much like a property, and the types of the literals that you can have correspond to XML data types. You can also have in the object position an IRI. And when you have an IRI in the object position, it forms what you would think is an edge in the graph. So as you look across the bottom, you can see how I create a friend relationship where in the object position I use that IRI. So if we expand this example to a full graph that we looked at before, you can see how we can define that. Across the top, we have a set of triples which defines the node Bill or person 1. And the second triple describes the relationship, the friend relationship, when person 1 connects to person 2. And the third set of triples on the bottom describes the second node for Sarah. So this is an example of how you would build the same graph but in RDF. So going back to looking at the relational versus graph modeling, in this case, let's look at a fairly typical order system. On the left-hand side, you see a relational model, ERD. And on the right-hand side, you see a graph equivalent of that model. So let's look at some query examples to understand the differences here. So most of you are likely familiar with SQL. In this query, we want to ask a question here of, find the names of customers who purchased the Echo. So as we go through, we're performing multiple joins from the customer table to the orders table, to the order details, and ultimately to the product. Before applying a filter on the product name Echo, this is a fairly standard SQL query. Now, if we look at this in SPARQL, the declarative graph query language for RDF, rather than expressing the joins as you would in SQL, what you express is a set of triple patterns. So recall that RDF is made up of triples. So here's the first thing we express, is a pattern for the customer and the order. In SPARQL, the red variables that start with a question mark are used across the triple patterns to create the equivalent of joins in a relational schema. Here you can see we join the order to the order details, and finally we have a filter on the product name of Echo. So this is a SPARQL query example where we're asking effectively the same question about finding the names of customers who've purchased an Echo. Gremlin provides an imperative traversal language for the property graph. So to answer the same question, finding the names of customers who've purchased an Echo, in Gremlin we're going to do it as a graph traversal. So first we start with the product. So we find all of the vertices which have the label product. Then we filter on that name for Echo. Then we start traversing the graph. So we go out to the order details, to order, to customers, and we find the unique customer names deduping at the last step. So you can see here the differences here between these two types of graph models, but how you can use them to answer the same kind of question. So let's look now at a property graph and an Apache Tinkerpop social networking friend recommendation example. The technique that we're using here is a technique called Tradic closure. This is very similar to triangle counting. A triangle is the smallest fully connected subgraph in a graph. So the idea here is that of two people we have a friend in common, but there's not already an edge between them that would represent an opportunity to create a new triangle in the graph and could be the basis of a recommendation. So this is an example of a triangle or a fully connected subgraph where everyone already knows each other. But let's see if there's an opportunity to create these triangles and make new recommendation. So first we start with Terry, and we go out and find the friends of Terry. Then we go out and find the friends of Terry's friends. Now we see that there is not already a relationship between Terry and Sarah, so this represents our opportunity to make a friend recommendation. So we've looked at this graphically. Now let's look at this through a Gremlin traversal. Here's the overall traversal, but now let's step through it. First we find Terry, then we find friends of Terry. Then we go out and find friends of these friends, where there does not already exist a friend relationship with Terry. So this is an example of how we can use Gremlin and a property graph to implement a very basic recommendation mechanism using Tradic closure. Now let's take a look at an RDF knowledge graph example. So you'll recall that one of the features of RDF is that it uses these IRI mechanisms. So in this example, we're going to look at some information that represents companies and geographic locations. The company information is taken from something that Thomson Reuters provides, which is the PermID dataset. And the geographic information is taken from something called GeoNames, which is a publicly available dataset of geographic locations and code sets. And so here in the first example, if you look at the triple that we wanted to say, this particular company, we see the URI for, the company, and we'll see later that it's actually Netflix, has an incorporation relationship with a country, so Netflix is incorporated in the USA. So there are a couple of nice things to note here regarding RDF and the URI or RII formats. In particular, the standardization in the use of these identifiers helps you interchange data with external systems. And so that's one of the features that we see most frequently across RDF applications. Now to take this example a little bit further and look at just a single triple, you'll see here we have this, again, the same statement shown. Now what we want to look at is adding the property. You'll recall that properties are literals in RDF, which correspond to XML data types. And here you can see that this is how we're expressing the name of the company. Now if we look at this example as a full set of triples, we'll see the first set of triples at the top, which represents the incorporation information. The next set of triples, which describes the name attributes. In this case, we're also adding phone information and we're pulling ISO country code at the bottom. So I mentioned the benefits of using IRIs or URIs, and one of the things that this enables you to do is create what is called linked data. So this is where you have different data sets which are owned and managed by different organizations, but you can use them to create new applications. So in this example, you saw that we're using the GeoName service to represent geographic information. We can also include things like Wikidata, which is structured information from the Wikimedia Foundation. By using these IRI concepts, we can guarantee uniqueness and identify the different data elements, and we can easily use them to bring things together. So let's look at some of the example of querying this kind of data. So you'll recall that SPARQL is the query language for RDF. It's a W3 standard and it's a declarative query language. Here we want to first issue a SPARQL query finding the name of a particular organisation with the URI. And so in this case, you'll see the select statement at the top, and you'll recall from the order example, the variables in SPARQL start with a question mark, and this query results in the name of the company being Netflix. So if we wanted to expand this out and look at all of the predicates and their values, we can do this sort of query pattern which you see at the top. So we have a URI and then we have two variables, the property and the node. And this results in all of the triples about that IRI. So we can see the name and the phone number and the location, and you recall the location is an IRI itself. So this can be further dereferenced. Now suppose we wanted to find the phone number for a company called Netflix. We can also express that as a triple pattern in SPARQL. So again, looking at this query, you'll see that the organisation name of Netflix, and we want to find the phone number. So this returns both the IRI for the company name Netflix as well as its phone number. Expanding this further, we could look to join this information with additional RDF datasets, such as geonames. In this example query, we take the isIncorporated country name and match this with the geonames dataset to include the ISO code in the query result. Here is a more complex example, also adding filters to the query results. Extracting the company name, Wikidata URI, and location from the PermID RDF graph dataset. Then filtering by companies with more than 1,000 employees, and then matching this with stock exchange information from Wikidata. Then finally extracting both the local English and Chinese names for the company. Given this introduction to knowledge graphs and how they can combine both public and private information to build a combined model and then query it, you can see how through this semantic web standard you can build very powerful new applications leveraging this data and relationships within it. So to recap, Amazon Neptune supports both types of graph models we explored today through examples of property and RDF knowledge graphs, along with their open API standards. It provides a high availability, ACID compliant with immediate consistent database service with support for up to 15 read replicas. It supports encryption at rest as well as enforcement of TLS, as well as it provides many database administration tasks such as backup and restore, point-in-time recovery, as well as fast ingestion from datasets hosted within S3. If you wish to continue your learning path with Amazon Neptune or any other Amazon Web Services offerings, there is online self-paced digital training, as well as in-person classroom-based training to support your education journey. There is also now a variety of learning paths and certifications to support your professional development. I would recommend, if you have not already done so, to visit the AWS training website to explore the various learning paths and formats now available. AWS has a wide partner ecosystem to help you focus on your success and take full advantage of the business benefits that AWS has to offer. Learn more about how APM partners can help you and find the right APM partners for your needs. Visit the AWS APM booth at our showcase. Thank you for attending today, and we look forward to your feedback on the session.